Hello and welcome to the Learn Electronics India channel. I am Meghna, and in this video we will be learning about operational amplifiers, also known as op-amps. While this is a vast and interesting topic of study, today we will just understand the basics of op-amps, its characteristics and applications. Let us get started to understand what an op-amp is. This is the general symbol of an op-amp, and this is how a one model of op-amp looks like. It is basically an integrated circuit. So inside this will be a circuit designed to perform certain functions. Originally, it was designed to perform some mathematical functions such as addition, subtraction, and it was also used to compare different values. While this still remains the fundamental function of an op-amp, it is still widely used for various purposes because of its versatile characteristics. I've written the same points in brief for reference. Coming to the characteristic of op amps, we have studied that amplifier is something that amplifies or increases the amplitude of a signal, be it in terms of power, voltage, or any other factor, which means it should have high gain. So that is one important characteristic of an operational amplifiers. It has very high gain and hence it is used to amplify the smallest of a signal. Another thing we usually prefer in electronic circuits is to save the amount of current that is being utilized by the circuit. So op amp has very high input impedance. This means that the current will be low because we have studied that resistance and current are inversely proportional. The same follows with impedance as well. So if input impedance is high, it indicates that the current that will be utilized would be very low. On the contrary, we expect the loss to be minimal on the output side, which means we require low output impedance, and that is also achieved by an op amp. Lastly, common characteristic of every op amp is the noise it suppresses. So wherever there is a lot of disturbance in the audios, during such cases, op amp is still suitable because of its characteristic of low noise. Apart from characteristics, we also have some basic principles for an op amp. Op amps usually amplify the voltage difference between its input terminals. That is like one of the very basic principle an op amp does. Another important principle would be its linear operation. So an op amp always maintains this linear mode by operating within the specified input and output ranges of voltage. And there is no distortion of the signals. These two qualities makes an op amp suitable for various functions. Virtual ground is something we imagine a particular terminal to be as ground or 0 volt. So when we call something as ground, it means the voltage at that node or that point would be 0 volts. So here we consider one of the terminals in an op amp to be virtually grounded, which means it is 0 volts. Doing this will make the calculations simplified and a complex circuit can thus be easily analyzed. That is the use of virtual ground. Negative feedback is when we give part of the output back as input so that it can improve the output according to the needs of the user. So this one feature is used in op amps, which improves the performance and improves the gain of an op amp. That is how higher gain is usually achieved in op amps. Next, we have applications of op amp, and in that, three important applications we'll be studying now is op amp as an adder, op amp as a subtractor, and op amp as a comparator. While there are many other applications, we will just understand these three to get a basic understanding of how op-amps can be used. So when op-amp has an adder, it means op-amp will add the inputs and it will give one single output at the output terminal or as V out. There is a lot of concept involved in analyzing this circuit, and we have multiple theorems like the superposition theorems and the basic laws in electronics which we studied to be used, apply KCL, KVL and other laws, and then we obtain this formula. This RF is mainly like a resistor that is being used in the negative feedback circuit, and Rn is the nth resistor of the nth input voltage. So after doing all the simplification and circuit analysis, we get a formula like this, which is used to obtain the output voltage. So internally, in layman terms, if we need to understand, adder will basically add the inputs and it will give one single output, that is the sum of all the inputs. The value of these resistors changes the formula and also the value of the output. Similar is the case with op-amp as a subtractor. While here it adds and gives the sum, in this case, it will subtract the input values and give the difference. This formula might look a little complicated, but it can further be simplified by taking R1 equals R2. You might have observed this inverting and non-inverting inputs. Inverting means it is basically the negative input or the negative terminal in this op-amp, and non-inverting input is nothing but the positive input. A more detailed concept of this is there in amplifiers, and there are non-inverting amplifiers and inverting amplifiers. So when an inverting amplifier, we give the input signal to the inverting terminal or the negative terminal, and in a non-inverting amplifier, we give the input signal to the non-inverting or the positive terminal. For now, you just have to understand that inverting means negative and non-inverting means positive. Moving ahead to a comparator, as the name says, it will compare two values. So it will tell whether one value is greater than the other, whether it is lesser than the other, or if it is equal to. This scenario is mostly also seen in digital circuits. So in that case, the output of the op-amp will change its state either high or low based on this relationship. As a beginner, we do not have to break our head into what exactly happens inside, but just understand how op-amp can be used to perform different mathematical operations. While these three were the basic functions of an op-amp, we have many other applications of it. Some include voltage follower, instrumentation amplifiers, and so on. We have studied in the previous video that instrumentation amplifiers are used in sensor and applications where there needs to be accuracy and precision. Integrator and differentiator, as the name says, it will give integral of the input signal and differential will give the derivative of the signal. Oscillators are something that generate periodic waveforms. So it is used in signal generation. Signal conditioning again includes removing noise and tuning the signal and various other multiple functions that together is considered as signal conditioning. Waveform generator, one example can be a PWM generator. So in such generators, op-amps are used to generate various waves like the square, sine waves, triangular waves. By generating these waves, various instruments would be tested. Lastly, let us recall what we have studied. So we have understood that op-amps works like an integrated circuit, and it is known for its high input impedance and low output impedance, along with high gain being a characteristic feature. We have also understood the different characteristics and basic principles of op-amps, followed by how op-amp is used as a adder, subtractor, and comparator. Lastly, we understood the different applications of op-amps. In the next video, we will learn about digital electronics, Stay tuned. Thank you.